Okay, we want to introduce the idea of vectors in this YouTube, and in particular we want to talk about displacement, which is the first example of a vector that we'll see in this class. So consider a snail, and imagine that the snail moved from point P to point Q. And left a slime trail as it moved, and so the displacement is going to be an arrow that we draw starting at the position it started and ending at the position it ended. And so there is two things associated with the displacement as with any vector, and that is going to be a magnitude, some length here, some certain number of centimeters, and some direction. And so we can say this is pointing so many degrees north of the eastward direction and is so many centimeters in length. So having introduced that, now let's say that the snail does something more complicated. Let's say the snail undergoes a displacement from P to Q, which we will call A. And now since A, the displacement A is a vector, we're going to symbolize that by using some letter to denote that it's a vector, and then an arrow drawn over the top signifying that it is a symbolic quantity and it is a vector. So A arrow, your book will generally use a boldface letter or designation. So the snail will go from P to Q with displacement A, and then it'll go from, let's say, Q to R with displacement B. And note that each one of these displacements has a certain magnitude. If each one of these little divisions is 1 centimeter, then this snail is going 3 centimeters due east, and then it's heading in a northeasterly direction here. And so the end result is of the snail, first of all, going a displacement A and then a displacement B, is that it ends up, the net result is that it starts at P and ends up going to R. And this is how we define the net displacement, simply as the addition of these two displacements. And note how the addition is defined. Basically, the two arrows are put head to tail, and then there's a new vector that's defined that starts at the beginning of the first vector and ends at the end of the second vector after they're head to tail together. This is called the net displacement. Okay, so that's vector addition, and I should probably say that. This is the graphical way in which we do vector addition. Now it turns out, and we'll talk about this as we go along here, one can also multiply vectors. We'll talk about how that works in probably the next YouTube, and we can also subtract vectors. So let's pose some questions here. I've got 3 examples, 2 of which are already written on here, and one extra one that I'm going to add. So let's say that we had a net displacement A, which went from 0 to this point here, as indicated, and then a first displacement A, and then followed by displacement B. And so what would the net displacement be of A plus B? And so perhaps I can choose a different color vector here, and I can draw this in as this vector right there. So this would be the net displacement if I took A followed by B. A vector displacement followed by B vector displacement. What would happen if I did it the other way around? Started at the same point O, but I did B first and then A second. So B is the same here as it is there, and A is the same here as it is there. I just basically do it in the opposite direction. Well, if I use the same definition for vector addition, I go from the start of the first vector, which in this case is b, to the end of the second vector, you will see that these two vectors are the same. And the conclusion is that a plus b is equal to b plus a. So the order in which one does vector addition is immaterial. It's the same as just adding numbers together. For example, we know that 1 plus 2 is equal to 2 plus 1. So although vectors behave differently than numbers, in this case they behave the same way. Okay, so let's now look at a third example here. So again, the same question, what is the net displacement? But in this case, what we're going to do is we're going to have a vector A that does this. That's my A vector. Let me change colors here so that we can see something that's a little bit different. And then you're going to have to imagine this B vector being right on top of the A vector. I won't draw it on top. I'll draw it displaced a little bit backwards. Up above, I should say. And there's my B vector. Okay, now if B was right on top of A, you should see that if I start here and I go there and then I basically turn right around and come back again, what I end up doing with the snail, if you want to personify these displacements with a snail, is the displacement is 0 in this case. So the snail went 1, 2, 3, 4, 5, 6 centimeters due east, and then went 1, 2, 3, 4, 5, 6 centimeters due west, and came back to where it started, and there was no net displacement. Okay, so in the next YouTube we'll talk about multiplying vectors and then subtracting vectors, because that's also going to be important for us.